Welcome student to this video where we will explore the relation between equivalence classes and the partition of a set A. So we'll assume we have a set A and we have an equivalence class tilde on A, then the set of all equivalence classes will form a partition of A. Of course, this theorem is only one side of the story where equivalence classes gives rise to a partition. In theorem number 2, it will be the opposite. If we have a partition, then we get an equivalence class where equivalence relation where the equivalence class are exactly the set of partition of A. So now let's focus on the first part where we are given a partition. So we will assume A, of course, non-empty set, and delta is an equivalence relation. Of course, if it's equivalence relation, we remember we have three identical story. I will just write them down here. We know that if A is equivalent to B or in relation with B, it means they are in the same equivalence classes. And we know that also the intersection between those classes is not empty. That's one of the information we know from the equivalence classes. So if we do the negation, if we write here empty, this would be not equal and they will not be in a relation. Now, what we need to prove, we need to show that A mod tilde is a partition. Now, for partition, just to remind you what a partition is, partition means those sets here, if we take the union, we get A. So we need to show exactly I, that the union of all equivalence classes, all of them, is equal to A. Second, if we take any two equivalence classes, different equivalence classes, the intersection is empty. Well, for the second one is easy because if they are different equivalence classes, it means they are not the same. We know that by number 3 here, it will be empty. So we need only to focus on the first one. So for the first one, what we are going to do, we will take any A in A, and we know that A must be one element of the equivalence class of A. Hence, or let's say I'll just change it to X. I will tell you why I change it to X in a minute. Just keep X. Hence, X is in the union of all equivalence classes. Thus, A is subset of the union. Remember, if I want to show two sets are the same, I need to show that each one is subset from the other. So I pick an element X in A, I do many steps, and I show that X here. Of course, the opposite will work in the same way. If we take any X here, it will be in one of the equivalence classes, and of course, their union must be part of A. Thus, A is just the union. Now, for the second, we will take two equivalence classes. They are not the same. Then by 3, their intersection is empty. Thus, the set A mod star A delta forms a partition of A. And that's the proof. The next proof is if we are given a partition, if we start with a partition AI, then we will define a relation between A and B by, if they are in the same partition, we will say they are in a relation. And we need to show that this is an equivalence relation. So in order to prove something is an equivalence relation, we need to first of all check if it is reflexive. Reflexive means is A related to A, which is the same question as ask myself, is A comma A belongs to the same AI? And the answer, of course, is yes. Why? Remember, because A is a partition. And a partition means A, it's only in one and only one set, which is AI. Second, symmetric. I'm using the idea of partition embedded here because partition means AI is different than AJ. Whatever in AI, they all in AI. Symmetric, if we assume A related to B, then B must be related to A. So I will assume A related to B. Hence, A comma B is in AI. And so B comma A will be also in AI. Remember, this is a partition. So B and A can be only in one set. They cannot be in different sets. So I'm sure that they are here. Thus, A comma B or B comma B tilde A. And the third one, transitive, which means if we have A related to B and B related to C, then we need to prove that A related to C. Of course, here is also straightforward because assume A related to B and B related to C. Now, this means A comma B must be in AI, and because B is in AI, C will also be in AI. Thus, everything is in AI. So, A tilde C. Of course, here we are again using the idea of the partition that any element is only in one of those AIs. And that's what makes this relation well defined. I exactly can't say if they are in the same set because it can only be in one set. Thank you for watching.